What science taught me about the paranormal. A physicist's journey into paranormal claims. What the data reveal and what they don't. In a 2022 BatGap interview, it was argued that rejecting the paranormal reflects an absurdly narrow view, and that some critics refuse to read certain studies. I did read them, and I tested the claims. I published MicroPK experiments, and I reanalyzed a large MicroPK dataset using new methods. I also carried out a forensic analysis of a related 2012 double-slit experiment study. So what does science actually teach us about the paranormal? To explore this question, I examined one specific experimental claim: micropsychokinesis. Micropsychokinesis, the alleged human ability to influence the statistics of a random process by thought alone. In 1991, I conducted my first MicroPK experiment using the Schmidt electronic RNG shown here. The device was designed to test whether intention could bias a random physical process, a proposed mind-matter interaction. 31 LEDs on top flashed in selectable patterns, controlled by a rear switch. At the end of each test, the front display indicated the outcome: a plus sign if the result aligned with the pre-specified direction of intention, and a minus sign if the outcomes predominantly deviated from it. My protocol was to run a fixed number of observed trials in a given machine mode, while the participant attempted, mentally, to influence the sequence of lights. This was followed by an equal number of unobserved trials in the same mode, with the device running unattended while the operator was elsewhere. Scores were recorded manually, which can introduce recording and transcription errors. Most, but not all, participants completed the full set of observed and unobserved trials. My first MicroPK test produced a distinct result: the cumulative z-score, how many standard deviations the total score deviated from chance, was positive for observed trials. It was negative for unobserved trials. I referred to this pattern as the balancing effect. When I resumed testing after returning the device, the balancing effect did not reappear. However, a small number of other parapsychologists later reported similar patterns under their own testing conditions. I later learned that my first tests used an RNG mode that mixed live random data with a pre-recorded internal sequence, which I regarded as a likely explanation for the apparent balancing of z-scores. My attention then shifted to a larger, 3-laboratory investigation. In the late 1990s, a coordinated effort was launched to replicate the reported evidence for micropsychokinesis, MicroPK. 3 laboratories conducted a pre-specified series of experiments. 1. Peer Lab in USA. 2. Institute for Frontier Areas of Psychology and Mental Health, IGPP, in Germany. 3. A lab at the University of Gießen, Germany. All 3 laboratories reported results that did not support the MicroPK hypothesis. I applied resculled range analysis to the FAMMI time series to test whether the data show long-term memory. The method estimates the Hurst exponent, h, which indicates whether successive values in a sequence of supposedly independent measurements are in fact correlated. For independent values, the Hurst exponent is 0.5, within statistical uncertainty. Values above 0.5 indicate persistent correlations between successive measurements. I applied rescaled range analysis to collected data sequences: under focused intention, experimental, under no intention, control, and those recorded over long periods of time while the RNG ran unattended, to assess the device's intrinsic randomness, the calibration data sequences. The experimental sequence showed a weak departure from the random expectation. After shuffling the experimental sequence, this weak departure from randomness was reduced. The control sequence showed similarly weak departure from randomness, comparable to that in the shuffled experimental data. By contrast, long unattended RNG calibration runs behaved as expected for random data, supporting their suitability for these tests. The FAMMI MicroPK time series did not support the microPK hypothesis. The weak correlations observed are most plausibly explained by differences in the data sampling procedure, as the animation illustrates. The results were published as a project report titled Application of Alternative Mathematical Models on PK, REG Data, a Study of Fractal Character in Records of PK Data. Subsequent peer-reviewed publications also followed. Such artifactual correlations may have encouraged later interpretations that the data reflect genuine underlying effects, for example, psychological or nonlocal, although these interpretations lack independent support. After the failed 3-lab replication, the question was no longer how micropsychokinesis, microPK, works, but whether it exists at all. In response, the IGPP launched a project to compile and analyze a comprehensive database of all microPK experiments that used true random processes, later known by the initials of its 3 authors, the BSB meta-analysis, or BSB-MA. To aid their evaluation, the BSB produced the database's funnel plot, which contained all essential information about the large microPK database. The funnel plot of the large microPK database graphically revealed the range of experimenter biases that shaped the database in such a way as to generate a weak deviation from chance where there was none. Let us examine this evidence more closely. Each of the 380 points in this funnel plot represents an individual microPK study, analogous to my early tests with a Schmidt-RNG. In this metaphor, 62 investigators used a true random process of their choice to collect a total of n lead steps each, while attempting to mentally influence the outcome. The proportion of positive steps represents effect size, p, of each study, ranging approximately from 0.35 to 0.75 across the database. The total number of steps, trials, in each study, n, ranged from several tens to nearly 1 trillion. With only 2 possible outcomes, positive or negative, the expected proportion of positive steps under chance is 0.5, or 50%. Effect sizes, p, above 0.5, are interpreted as evidence in favor of the microPK hypothesis. The larger the deviation, the stronger the claimed evidence. The 380 microPK studies in this meta-analysis database were conducted over a period of about 35 years. Some investigators also conducted 137 no-intention control studies, which the meta-analysis authors made also publicly available. This allowed me to construct the corresponding funnel plot for the control data, where p on the x-axis again represents the proportion of positive steps across a total of n control lead steps. Let us now evaluate the evidence. The most representative outcome in both the experimental and control databases is the chance expectation, 50%. In the control funnel plot, this is expected. It confirms that the random processes used in the studies behaved genuinely randomly. In the experimental database, convergence toward 50% leads to the same conclusion already indicated by the independent 3-laboratory replication. The most representative microPK result is chance. Both funnel plots, however, indicate that the data are affected by publication bias. Results considered unfavorable tend not to appear in the literature, either because experimenters do not submit them or because journals do not publish them. A direct consequence of publication bias is an asymmetrical spread of data around the point of convergence, which is chance, 50%. In the MicroPK database, studies with fewer than about 100,000 trials are disproportionately distributed above 50%, creating the impression of weak supportive evidence. In the control database, studies fewer than several tens of thousands of trials are disproportionately distributed below 50%. In this case, some experimenters may have been concerned that control results above 50% would cast doubt on the adequacy of their random system. The asymmetric spread of the data shifts the statistical average below 50%, even though the underlying processes are purely random. Because each study represents an independent estimate of the same hypothesis, the results should be randomly distributed around the convergence point and appropriately confined within the 95% confidence interval curves expected for random data. Appropriate confinement means that only about 5% of studies should fall outside these limits purely by chance. In the MicroPK funnel plot, however, far more studies lie outside the 95% confidence interval curves than expected. In the control database, although it contains fewer studies, the results cluster too closely around the center and do not spread outside the 95% confidence limits as expected for random data. Both patterns indicate that the results are not independent random outcomes. We therefore examine possible sources of systematic bias in the database. The clear excess of studies beyond the right-hand confidence limits, consistent with errors that favor the tested hypothesis, indicates the presence of experimenter effect bias. The clustering of studies on the opposite side indicates conformity bias, where experimental errors cause new results to resemble outcomes previously reported in similar studies, even when those outcomes contradict the tested hypothesis. Although conformity bias is present throughout the database, it becomes most visible on the outer left-hand side of the funnel plot, where reported scores deviate significantly from chance against the tested hypothesis. In the control funnel plot, the presence of both biases is reflected in the almost non-existent number of studies falling outside the confidence limits. Rescaled range analysis of the MicroPK and control time series confirms that conformity bias is present in both databases. The 380 MicroPK and 137 control scores were aligned by publication date as closely as possible and analyzed as time series. The Hurst exponents of both time series remain clearly above the 50% baseline, indicating persistence, with hits tending to follow hits and misses tending to follow misses. After repeated shuffling of the time series, the Hurst exponent drops to the baseline level. The long-range correlations, where later results tend to resemble earlier ones, disappear, indicating a pattern consistent with conformity bias. Conformity bias in both databases was further confirmed by detrended fluctuation analysis, DFA. The ordered sequences displayed characteristics consistent with persistent correlations, whereas shuffling removed those characteristics. This persistence of binary scores, or of trends, increases the scatter of the data around the point of convergence and broadens the MicroPK funnel plot, rendering the standard confidence limits for random data inapplicable. The evidence therefore shows that confidence interval curves derived for random data cannot adequately describe the spread of biased datasets. To address this, I derived confidence interval curves for biased binary processes, extending the probabilistic framework discussed by Richard von Mises for two-state Markov sequences. The 95% confidence curves for biased processes successfully envelop the data as expected, while providing a numerical estimate of the strength of the equivalent biasing process. This framework mathematically describes the combined effect of errors contaminating the database. The framework has been successfully applied to study primate-handedness. It has also accurately reproduced Markov's 1913 statistical analysis of vowel and consonant sequences. The MicroPK and control databases show an additional pattern linked to the three biases. Early reports in both datasets deviated strongly from chance, while later results moved closer to chance. Importantly, this regression occurred in opposite directions. MicroPK data decreased toward chance. Control data increased toward chance. The unequal rates of regression indicate that the same influences act with different strengths in the two datasets. A plausible interpretation is that experimenter bias raises MicroPK scores above chance, while control scores are influenced in the opposite direction, reducing the likelihood that they resemble MicroPK outcomes. This pattern suggests a gradual improvement in experimental protocols, reducing, but not eliminating, the influence of bias over time. The two trends converge at chance, 50%, around 1993. The negative regression of MicroPK results toward chance is known as the decline effect, a statistical pattern, not a physical phenomenon. The convergence around 1993 does not correspond to a specific event or methodological change in the literature. Rather, it reflects the point at which two long-term trends, driven by gradual reduction of bias, intersect. The year itself is therefore not causal, but an emergent property of the evolving datasets. The large three-lab replication of the MicroPK hypothesis produced negative results. The subsequent meta-analysis of the large MicroPK database confirmed the same conclusion. There was no evidence that the mind, through intention, attention, or consciousness, directly influences or modulates physical reality or the statistical outcomes of independent physical events. With this hypothesis no longer supported by experimental evidence, new ideas began to emerge to sustain the belief that the mind affects matter. Among the emerging ideas, some researchers began invoking quantum theory to support new experimental claims. Let us now examine these ideas. In 2012, a MicroPK-related claim appeared in the literature, presented in the language of quantum physics. A double-slit experiment was reported as evidence that focused attention could collapse the photon wave function. I examined this claim through a forensic analysis of the reported experimental setup, of the kind commonly used in standard physics teaching laboratories. These are the two key graphs reported in the publication: the interference pattern and the fast Fourier transform power spectrum derived from it. Together, they reveal several internal inconsistencies. The reported experimental parameters were inaccurate and inconsistent with the two published graphs, although they should have been mutually compatible. The information conveyed by the two graphs was itself internally inconsistent. In addition, the fast Fourier transform spectrum displayed unnatural features. Finally, the graph presented as the central evidence could be replicated computationally after applying deliberate spectral shifts. Taken together, these findings show that the reported description could not have originated from a real double-slit experiment. My forensic analysis showed that the effect attributed to observer influence does not depend on the presence of a subject. The same conclusion was reached independently through a statistical analysis of the data generated by the same experimental setup. As the reported physical effects in MicroPK studies gradually declined toward chance, increasingly less testable explanations were introduced to preserve the underlying hypothesis. Rather than treating the disappearance of the effect as evidence against mind-matter interaction, some authors proposed that the interaction might persist in another form, not as a measurable physical effect, but but as a kind of non-local correlation linked to psychological variables. In this reformulation, the phenomenon is no longer expected to produce a stable shift in the statistical average, yet it is still said to exist in ways that cannot be reliably replicated. This move changes the claim from a testable physical hypothesis into something much harder to falsify scientifically. At that point, the situation begins to resemble the idea of little green men on the far side of the moon who always hide whenever someone tries to observe them. Such a claim may be protected from refutation, but it no longer functions as a normal scientific hypothesis. Quantum ideas entered C research early. In a 1991 co-authored paper, quantum non-locality was proposed as a possible mechanism for telepathy. Although the idea was explicitly speculative, it was later treated in some discussions as though it offered a theoretical basis for paranormal phenomena, and the paper became widely cited in related circles. So, what has science taught me about the paranormal? Large-scale replication, a much larger meta-analysis, and an unconvincing claim framed in the language of quantum physics together provide ample reason to conclude that, so far, consciousness-related effects on physical reality are not scientifically supported by evidence. Quantum theory narratives may appear attractive as a way to fill that explanatory void, but they remain scientifically unsubstantiated. The data instead suggest that experimental results can be unintentionally distorted by bias-driven errors, a tendency that seems to have declined over time but not disappeared.
As Richard Feynman described in 1974,
they do a lot of experiments, and even though they may get a certain result, they gradually eliminate things and improve the techniques. The effects get smaller and smaller and smaller until they gradually disappear.